Okay, we're returning to 5.5 curve sketching. Example number 4, part D. Suppose the graph below is the graph of a function y equals f of x on the interval from -8 to 8. On the same set of axes, sketch and label a possible graph of f prime in red. All right, so one thing you do want to remember that if you are thinking about this, you've got concave up all the way to here at -2. So your second derivative is going to be 0 at -2. So that means that your first derivative is going to have a max or a min there. And since it's going from positive here to, well, it's going from concave up to concave down at this point right here. Sorry, I'm pointing at it and you probably can't see it, but I'm talking about that point right there. You have to remember that it's going from concave up to concave down. That's a plus to a minus. You're going to have a maximum on your second derivative that will account for this point of inflection there, okay? You've got another point of inflection right here, and it's going from concave down to concave up, so this one is going to be a minimum at 2. So a maximum at -2 and a minimum at 2 for your first derivative, because that will be how you get that point of inflection on your second derivative, okay? And actually, you're going to have another one here, another point of inflection where it goes from concave up to concave down. So you might want to think about for f prime of x, okay? At x equals -2, you're going to have a max. At x equals +2, you're going to have a min. And at x equals 6, you're going to have another max, okay? So that was one thing that I did want you to think about whenever you're sketching the graphs here. And I'm just going to erase those. Another thing, you should be thinking like slopes of tangent lines here, so all these slopes are negative and then they go to 0, okay? So you actually have a 0 here on your first derivative graph. And then you have, so it's going to start out negative, okay? It's going to start out negative, and it's going to go to here, and then it's going to start being positive, because look, positive slopes, positive slopes, positive slopes. And then remember what I said, we've got a maximum at -2. So you're going to come up to a maximum at -2, and then you have positive, you still have your slopes of your tangent lines are still going to be positive. Positive to here at -1. But what happens at -1, you've got a 0. So, because your slope of your tangent line is going to be 0, so it's going to stay positive. All these are positive slopes until you have the slope of 0 here at -1. And so then you're going to go down and you're going to have a minimum at 2. And then you'll have your 0 here at 4, because look, slope of the tangent is 0 again. And then getting ready for your maximum here at 6, and then back down to 8, okay? Where you'd have a slope of 0 there if it kept going, it looks like, okay? So that is about what that derivative would look like, okay? For part E, if the graph below is the graph of the derivative y equals f prime of x on -8, 8, sketch and label a possible graph of f of x. So now we're going the opposite, and this gets so confusing. So bear with me here, because if this is the derivative, okay, so you're looking at the derivative here, that means that you have a derivative of 0 here, but it's not a max or a min because it goes from positive to positive. Okay, so that's going to be like a horizontal tangent. So you've got positive slopes of tangent lines, 0, and then more positive slopes of tangent lines. You don't have another 0 to here. This is going to be a max at x equals 2. So for f of x, which is what we're trying to draw, at x equals 2, we're going to have a max. Okay, at x equals 6, we're going to have a min. You can see that it's 0 for the derivative, and it goes from negative to positive, therefore it's a min. Here it went from positive to negative, it's a max. And we said that at x equals -5, we're going to have a horizontal tangent. Because it is 0, but then it almost looks like this, where it flattens out, but then goes like that, right? So it's 0 for a brief moment, but the slopes of the tangent lines are still positive on either side. So, what else do we have to think about? Oh, for the second, if this is my f prime of x, my second derivative would have a 0 here, and it would be going from positive to negative. So therefore, I have a point of inflection here. This tells me I have a point of inflection at x equals -1, it looks like. And so we need to make sure that we have a point of inflection. And you can actually think about, if this is the derivative, and you're thinking about, well, if I took the derivative of it, I've got negative, 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 0, positive, 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 all the way to here. So you're talking about, for your original function, you're going to have negative, 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 0. From -8 to -5, you're going to have concave down. Okay, so that's going to be concave down. So -8 to -5 is concave down. And then you've got, you know, your horizontal tangent. And then you've got positive slopes of tangent lines all the way to here. So you've got from -5 to -1 is concave up. Because those are the slopes of the tangent lines for the second derivative. We said that there was a point of inflection here, and then that means it's changing from concave up to concave down. So we've got from -1, negative, 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 all the way to 4, concave down. And then again, you've got, you know, slope, and it goes from negative to positive. This is another point of inflection. So you've got a point of inflection at x equals, let's put this, point of inflection at x equals -1 and at x equals 4 for your, and we're still talking about f of x here. Positive, 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 and then at the end it's 0. So that means that concave up from 4 to 8. So we need to make sure that our f looks like that. So I'm going to try and just erase everything that I did here so that we can sketch a graph of our original function from this derivative. Okay? All right, so now this is going to kick in a minute like it normally does. We said concave down from -1 to 8, and then horizontal tangent. Okay, oops, sorry. So concave down, horizontal tangent at -5, okay? Then it should go up. We're going to have a point of inflection here. So about right there, it's going from being concave up, because we said it was concave up from -5 to -1. And now it's going to have to start going to concave down. It has a maximum at 2. And I think I just missed that. Sorry about that. I kind of missed it. I'm going to have to erase a little bit. Oops. Maximum at 2, and then a point of inflection at 4. That means you've got, it's starting to go like that. We've got a minimum at 6, and hopefully that 4 is like a point of inflection here. Minimum at 6, and then back up, okay? And then we stop, okay? I don't know if this, you know, we just stop there because we don't know. It looks like again, it looks like a slope of 0, but we're not sure. So it could be another, like going from positive, positive, could be another max, but we don't know because it stops there. But that would be, you've got your point of inflection at 4, you've got your maximum at 2, you've got your minimum at 6, point of inflection here at -1, where it, see how it goes concave down, concave up, concave down to here, and then concave up for the rest of the way. So anyway, that looks like a good, oops, not f prime, we had f prime. That looks like a good f of x that we drew there, okay? All right, so that was a little bit of curve sketching there, what the whole lesson's called. Now, guidelines for analyzing the graph of a function. The first thing you do is determine the domain, intercepts, asymptotes, symmetry of the graph. Then you're going to find critical points and intervals where the function is increasing and decreasing. Then you're going to determine local maximum and minimum points. Then determine concavity and find points of inflection and sketch the curve. So for example number 5, analyze and sketch the graph of g of x equals x plus 2 times x minus 1 squared. So we're going to find the x and y intercepts. And remember, your x-intercepts are going to be where your y is 0, right? And your y-intercepts are going to be where your x is 0, okay? So if I want to find my x-intercept, I'm going to set y equal to 0. Well, if I set y equal to 0, that's going to enable me to use the zero product property. I know -2 would make it 0 and +1. So -2 would make it 0 and +1. So therefore, my x-intercepts are -2, 0, and 1, 0. My y-intercepts, that would be found by making my x equal to 0. So 0 plus 2 times 0 minus 1 squared would give me 2 times -1 squared, which is going to be 2. Okay, there's only one y-intercept. Find the first and second derivatives, okay? So if I was going to find the first derivative, I would take the first, because I'd have to use the product rule. This is f of x times g of x. So I've got f of x times the derivative of the second. So the derivative of the second, I'd bring the 2 down, times x minus 1 to the 1, times the derivative of x minus 1. And then plus the second times the derivative of the first. So if I was going to simplify x plus 2 times, and I'm going to go ahead 2x minus 2, I just distributed that 2 to that x minus 1, plus x minus 1 squared. So 2x squared minus 2x plus 4x minus 4 plus, this is going to be x squared minus 2x plus 1. So that gives me 3x squared. The two x's are going to, or all the x's are going to go away. And then a -4 and a +1 is a -3. And if I wanted to, I could factor that 3 out. And this would be 3 times x minus 1 times x plus 1 if we needed it, right? And then my g double prime of x, of course, I'm going to use this one for my g double prime because it's the easiest one. So that's going to be 6x, okay? Bring that 2 down times 3x, and then the derivative of negative 3 is just 0, okay? So I found my first and second derivatives. I'm going to complete a sign chart for g prime of x to find intervals where g of x is increasing and decreasing. So we're looking at the sign of g prime, and we're using our when we set that first derivative equal to 0 to find our critical points, we would get x equals 1 and x equals negative 1. So again, you put the negative 1 on the left because it's less than, put the positive 1 on the right, just like on the number line. We're going to put a number, I'm going to say negative 2, into my derivative. I would get 3 times a negative, which would give me a positive. If I put a 0 in, I'm going to get negative. And if I put a 2 in, I'm going to get positive. Okay, so there's my sign chart for g prime with my critical points from my derivative and the sign. This tells me that my regular function g of x is increasing from negative infinity to negative 1, decreasing from negative 1 to 1, and increasing from 1 to infinity. Okay, so that helps me when I'm going to sketch this graph. So like I said, I have increasing from negative infinity to negative 1, also from 1 to infinity, and then decreasing from negative 1 to 1. So determine any relative extrema. Well, if I go from plus to minus, I have a max at negative 1, and I have a min, because I go from negative to positive, at positive 1. Okay, so I have a local max at x equals negative 1, local min at x equals positive 1. Complete a sign chart for the second derivative to find intervals where g of x is concave up or concave down. So if I set this one equal to 0, I see that my critical point is x equals 0. So I'm going to be looking at the sign of g double prime of x on either side of its critical point, 0. So I'm going to put a negative 1 in, I get negative. Put a positive 1 in, I get positive. So you can see that we have concave up from 0 to infinity, and we have concave down from negative infinity to 0. Since it changes signs at 0, 0, 2 is my point of inflection. Okay, because remember, if the second derivative changes signs at the critical point, then you have a point of inflection there. And I remembered that when I put 0 in up here, that I got 2. So I just glanced up there and saw that, and I was like, oh, otherwise I would have had to gone back to my original function to actually find out what that point is. And now we can sketch a graph. So we know at 0, 2, we have that point of inflection, okay? We know at negative 1, we have a max, and at positive 1, we have a min. So with this being a point of inflection, it's probably going, well, hold on, because I kind of missed my negative 1 there. This eraser does not like me. So let's try this again. Sorry guys, I hope that you are having a better time on your own paper than I am. So we'll put a maximum at negative 1, and if that is my point of inflection and I've gone up to 4, so basically I've gone 2 away, I have to go 2 away this way, and then this way, like that, because that point of inflection is right in between. Now let's make sure that this works. So we have increasing from negative infinity to negative 1, that works. decreasing from -1 to 1, and then increasing again from 1 to infinity. Okay, that works. Concave up from 0 to infinity. So from 0 to infinity, concave up, and from -infinity to 0, concave down. That works. And I've got my point of inflection. So this is a good graph. Yep, that's a good graph of that function. It ends up being a cubic function, right? Because we have x to the second up here, and times x to the first. So that gives you x to the third. All right, so now example number 6. The graph of y equals f prime of x is shown below on the interval from -8 to 8. If f of -8 is 5, if f of -8 is 5, on the same set of axes, sketch a possible graph of the function y equals f of x. So they're telling us here that this is your derivative, okay? And they also told us that if we're trying to sketch, I'll just do this in a different color, we're trying to sketch f of x. And they told us this point. So I'm going to go to -8 and then up to 5, and I'm going to start right there. That point I know is on the graph that they want me to draw, okay? And I have to figure out things about f of x based on the derivative. So I know that at x equals, let's just think about things that we know about f of x from the derivative, f prime. We know that the derivative is 0 at negative, oh, I can hardly see that. I better make it bigger, at -5. And the derivative goes from negative to positive. So at x equals -5, we have a min, okay? Also, remember, if this is the derivative, and if we are imagining the slope of the tangent line being 0, and it be going from positive slopes of tangent lines to negative slopes of tangent lines, this is going to give me a point of inflection on the original function at x equals -3. So x equals -3, you have a point of inflection. And again, it's going from positive to negative, okay? So that means that from -8, positive, -8 to -3, you have concave up, and then negative all the way to +1. So from -3 to +1, you have concave down, because those are the slopes of the tangent lines of the derivative. Now here, you've got another point of inflection on the original function at x equals 1. So x equals 1, you have a point of inflection. And so this also starts to be concave up now because the slopes of the tangent lines are positive. So we've got from +1 to positive, it goes to 0, and then it goes positive again. So from 1 to 8, concave up, okay? With a brief little, looks like a slope of 0 here, real quick, at x equals 5, okay? Which, for that one, since you've got positive, and it is not a point of inflection, okay? So that would not give you a point of inflection because the second derivative does not change signs. So now, again, I have to erase this. I'm so sorry. It's hard to talk about these graphs without starting to sketch things and show you things. Henry, stop. All right. So now, let's go ahead and try to start sketching a graph. We know that we're going to have a minimum. Well, we know we have concave up, and we're going to have a minimum at -5. So let's just, oops, where did my graph go? Oh, I'm still on the, sorry. I got to put my point on there again. I was still on the eraser. So we've got concave up, to negative 5, and there's a minimum there, okay? Concave down, oh wait, I put concave up from negative 8, oh okay, minimum there, it's still concave up, point of inflection at negative 3. So at this point right here, at negative 3, it starts to be going concave down now. And you've got, do we have any more maxes or mins? At negative 1, we were going from positive to negative. So we had a maximum at negative 1 that I forgot to write. X equals negative 1 max. Sorry about that. So we'll erase that a little bit. So at x equals negative 1, we have a max. And then at x equals positive 1 is another point of inflection here. And then we go to going from negative to positive, we have a minimum at 3. Minimum at 3. When we have like a second derivative of 0 there, but it doesn't change signs, imagine that your slopes of your, imagine that your derivative is 2 at 5, okay? So it's getting closer and closer and closer to 2, then it's increasing, the function's increasing, and then it still continues to increase. So there is some sort of hiccup here, but it's not anything that, oops, I forgot that we're supposed to stop at 8. So there is a little hiccup there in the graph, but nothing that, like all your slopes of your tangent lines are still positive. Okay, so it didn't give you a point of inflection. You should have still been concave up. It was just kind of a little hiccup, okay? Which you can't hardly see what I did there. So I apologize for that, but and it could have been like even a piecewise function where, it kind of stops there, but it would have had to still been differentiable because it still had a derivative there. All right, so now the function f of x is defined and differentiable on the closed interval negative 6 to 6. The graph of y equals f prime, the derivative of f, consists of 3 line segments and a semicircle shown in the figure at the right. For each question below, find the values for y equals f of x on the interval from negative 6 to 6 and justify your reason. So now, find the x-coordinate of each critical point, okay? So let's just remember, this is our derivative, and so if you have a critical point, it would be where your derivative is 0 or undefined, okay? So I see a 0 at negative 4, 0, and 6, okay? Well, 6 is an endpoint, so let's just look at x equals negative 4 and x equals 0. And these are where your f prime of x equals 0. We're not going to include the endpoints. Find the x-coordinate of each relative extrema of y equals f of x and label as a max or a min. So we know that we had extrema at x equals negative 4, and since our derivative was going from negative to positive, so f prime of x changes from negative to positive. So x equals negative 4 is a minimum. Or you could put relative minimum. And then your 0, it goes from positive to positive. So that's not going to be considered an extremum. It's a critical point, but it's not an extremum because it doesn't change from positive to negative or negative to positive. So really, this is the only one for part B. For C, find the open interval over which the function y equals f of x is increasing or decreasing. Well, if we're looking at the derivative, we know that where the derivative is negative, which is from right along here from negative 6 to negative 4, that's going to be where your function f of x is decreasing. So we're going to say where f prime of x is less than 0, f is decreasing. And then I put decreasing negative 6 to negative 4. Where f prime of x is greater than 0, f is increasing. And so I put increasing intervals. Well, it's increasing from negative 4 to 0, and also from 0 to 6. Find the x-coordinates of each point of inflection. So remember what we talked about for points of inflection. It's going to be where your derivative is undefined or 0. I'm sorry, the slope of the tangent line of the derivative, right, is undefined or 0. So I can see that at x equals negative 4, if I was taking the derivative of this function, it's a corner, and so it would have an undefined point there. So I know that we need to start thinking about, and if you want to, we can just like make a little list over here, your f double prime of x, right? Because this is f prime, so the derivative of f prime is f double prime, is undefined for x equals negative 4. And then we would have the slope of the tangent line 0 at negative 2. So x equals negative 2. It's going to be f double prime of x is going to be 0 at that point. It would be undefined again at x equals 0. Undefined again at x equals 4. Okay, and those are all, not including the endpoints. So if we wanted to, then we would be making a sign chart for our f double prime. And it looks like we've got negative 4, negative 2, 0, and 4. And so I can see that it goes from negative, positive slopes of tangent lines, right? So look, positive, 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 because we're talking about the second derivative. And then it stays positive, positive, positive. So this is plus, plus. So this is not going to be a point of inflection at negative 4. Then it goes to 0. Then it goes minus. From negative 2 to 0 is minus. And then it goes plus again from 0 to 4. And then it goes minus after 4. So this is going to be a point of inflection because it changes from plus to minus. This is going to be a point of inflection, changes from minus to plus. And this is going to be a point of inflection, changes from plus to minus. So the x-coordinate of each point of inflection is what we need to put in here. So we've got x equals negative 2, because f prime of x changes from positive to negative. And guys, I'm just going to squeeze plus to minus, but hopefully you're writing positive to negative. We said at x equals 0 is where our f double prime changes from negative to positive. And at x equals 4 is where f double prime of x changes from positive to negative. Okay, that's your justification. Find the intervals over which the function y equals f of x is concave up or concave down. Well, we kind of just did that because of the sign chart we just made for f double prime. So we're going to say f double prime of x is greater than 0. That means that f is concave up, and that would be from -6 to -4. From comma -4 to -2, comma, and 0 to 4. You could put union in there if you wanted to. I just put commas for some reason, but you could have put union in there also if you wanted to. But those are all your intervals where f of x is concave up. So, you know, right here, the -4, there's something going on there. We don't really know what it is. It does have a derivative of 0, but it's not a point of inflection. So, you know, for a brief moment there, it's not concave up, but I could see that some might say that this is from -6 to -2, okay? It depends on what the function is, but we're going to break it up because we don't know. And then f double prime of x is less than 0, means that f is concave down. And that's going to be on the intervals from -2 to 0 and from 4 to 6. Okay? And again, you are just trying so hard to remember what all these things are doing. I know that you guys are probably going to have to go back and, you know, remind yourself, okay, when this happens, that means this, and things like that, to get your, you know, as you're getting used to drawing these graphs. Let h of x be a function that is continuous on the interval from 0 to 6. The function h is twice differentiable except at x equals 3, where the derivative of h does not exist. The function and its derivatives have the properties indicated in the table below. Use the table to sketch a graph of y equals h of x. So for this one, I found a couple of mistakes. So let's get these mistakes fixed first on your paper. That should have been a 2. This should have been a 2, and that should have been a 3. This 4 should have been a 5, and this 4 should have been a 5. So I did find some mistakes there. So let's correct that. And I also found that this was 1 and that this was 0. Okay, so that -4 should have been 1, and this 2 should have been a 0. Okay, so now we know we have the point. The first thing I'm going to look at is right here. I see the point 0, 3. Okay, so I'm going to sketch that point. I see the point 2, 0. I'm going to sketch that point. I see the point 3, -3. I'm going to sketch that point, and I also see the point 5, 0. So I'm going to sketch that point, okay? So now, the next thing I notice is that in between 0 and 2, I have it. All of my h values are positive. That means, of course, it's going to stay above the x-axis. My derivative is negative. That means it's decreasing. So it's a decreasing function from 0 to 2. And my second derivative is negative. That means it's concave down. So I am pretty confident that I can draw that, and that looks like a piece of the function. Then I go here between 2 and 3, and I have to figure out what's going on, okay? It's all of my function is below the x-axis, which makes sense. That was my negative here. If my derivative is negative, that means it is decreasing, okay? So again, I have a decreasing function, but this time my second derivative is positive, so that means that it's going to concave up here. And I didn't do a very good job of transitioning there, but it needs to go like from concave down here to concave up here, okay? So try and draw that a little bit better than me. Then we look from 3 to 5. It's all below the x-axis because my h of x is negative. My derivative is positive, that means it's increasing. My second derivative is negative, that means it's increasing but concave down. So it's going to look like that between 3 and 5. And then between 5 and 6, it's above the x-axis, and the derivative is positive, that means it's increasing, and my second derivative is positive, that means it's concave up. Okay, it did not give us a point at 6, did it? No, it did not. So we're just going to go concave up. And I think I ended it at 6.2 on my paper. I don't know if there was, did it give us 6.2 somewhere? No. Anyway, we can end it at 6.3 on this one. Why not? Because that's what I just did. But that is how you would sketch it. I almost like these better. Just because, I don't know, that was really organized, and you could really just, you know, do it in the intervals. Okay, so example number 9. The function f is defined and differentiable on the closed interval from -6 to 5. The graph of y equals f prime of x, the derivative of f is shown in the figure, and the horizontal, and has horizontal tangent lines at x equals -3 and x equals 2. Find the x coordinates of each relative extrema on the interval from -6 to 5 and identify them as a max or a min. So the nice thing about this is that when you are looking at the derivative, you are looking to see where the derivative is 0 or undefined, okay? So I see critical points here. So if I knew my original function and I took the derivative and then I set it equal to 0, my critical points would be x equals -5, and I'd make my little, my little sign chart. X equals -5, x equals 0, and x equals 4. Those are the critical points for my on my first derivative. And so it goes, look, these are all positive, and these are negative. Like they're above the x-axis, so I just put a little plus and a minus. And then, they stay negative all the way to here, then they go to positive between 0 and 4, and then they go negative after 4. So when you're looking at the sign of your first derivative like that, at your critical points, whether, your derivative is 0 here or undefined, if it goes from plus to minus, you've got a max. If it goes from minus to plus, you've got a min. Plus to minus, you've got a max. So we're going to say that we have a max at x equals -5 and x equals 4. And we know that because f prime of x changes signs from positive to negative at these x values. Now, on the AP exam, I would not want you to put the plus sign and the minus sign. I don't know if they would like that. So make sure that you write the words positive and negative when you're actually taking that, if they're, if you've got a situation like that. Minimum at x equals 0, and you'd say because f prime of x is 0 and changes signs. So f prime of x is 0 at x equals 0 and changes signs from negative to positive at that x value. Okay? So we had our max, we had our mins. Find the x-coordinate of each point of inflection for y equals f of x and justify. So if we're looking at the derivative, our points of inflection are going to be like our 0, slope of a tangent line. So I'm seeing points of inflection at -3 and 2 because it's going from negative slopes to positive, positive to negative. So it's changing, so if I had my f double prime sign chart, I would have -3 as a critical point and 2 as a critical point. And look, the slopes of my tangent lines are negative as before -3 to the left of -3, then they're positive between -3 and 2, and then they turn negative again. So you can see that these would be point of inflections because they're going from negative to positive, positive to negative, which is exactly what we said. So F has points of inflection at x equals -3 and x equals 2 because f double prime changes sign from, I guess, I split this up on my paper and I said for -3 it changed from negative to positive, and then for +2, positive to negative. And you could say that respectively, I guess, if we put them in order like that. So F has points of inflection at x equals -3 and x equals 2 because F double prime changes sign from negative to positive and positive to negative respectively, okay? So that means negative to positive at -3 because it was slopes of tangent lines, negative to positive and then positive to negative at 2. And then part C, let g of x equal x cubed minus f of x. Find g prime of -3. Okay, so what I'm going to do is I'm going to move over here because I have just been doing a terrible job of showing my work and giving you space. But this is what they just gave us. G of x equals x cubed minus f of x, and they want us to find g prime of -3. Okay, so if I was going to find g prime of x, it would be 3x squared minus f prime of x. And so if I was going to find g prime of -3, I'm just putting a -3 in wherever I see an x. And now we just have to start figuring it out. So -3 squared is 9, so this is going to be 3 times 9, this is going to be 27. Now I have to go to this graph to find f prime of -3. And if I look, it's -6. Okay, I'm looking at it right there. And so f prime of -3 is -6. So that's minus a -6, which is a +6. So this answer ends up being 33. So if they asked us for g prime of -3, our answer is 33. Okay? All right, that was the end of it. And don't get too crazy or worried about this lesson. It's good practice, and I think it helps you understand like the relationship between f and f prime and f double prime. But, you know, I mean, with the situation that we're in, it's going to be a little bit difficult to test you on this, but they are on Math Excel, and so I will give you some of those sample problems on Math